My name is Sarah Burch, and I'm a PhD student at Oregon State University. This video identifies the burning questions that need to be answered in biochar applications in agriculture, soil science, water treatment, forestry biomass management, production, and policy to advance the sustainability of the biochar industry. Biochar is black carbon, created as a byproduct of thermal biomass conversion to heat and energy in an oxygen-limited environment. Biochar has shown potential to advance sustainability through green energy production, carbon sequestration, soil water retention, increased food and plant yield, waste management, and water treatment. However, not all biochar is created equal. Biomass feedstock and production conditions play a significant role in biochar characteristics. Therefore, applications should be tailored to site-specific conditions and matched with favorable biochar properties. Researchers and practitioners came together at US Biochar Initiative conference in August 2016 at Oregon State University to discuss policy, production, remediation, agriculture, and forestry biomass applications of biochar. This video highlights key questions identified in these fields from workshops, presentations, and interviews at the US Biochar Initiative conference.
So can you inoculate biochar with microbes? That's a great question.
This is our mine reclamation project, and it's not fully up and running yet. So you're really seeing science in action here. The Formosa mine was mined for copper and zinc in the 1990s, and then way back about a century now. In the 1990s, they did an insane amount of damage to the mine, and they were shut down in 1994. When they were shut down, water from the adit or the entrance of the mine got in the Middle Creek, which is a salmon-bearing stream, killed all life for 60 miles in the Middle Creek. To this day, there are levels of metal in those soils that far exceed any sort of acceptable standard by any federal agency. The soils have a pH of about 3, so they're very acidic. Now, the problem with the mine isn't necessarily the minerals, it's the microbes, because the microbes are what free up those metals and make them soluble. So in order to change that paradigm at the mine, we need to change both the soil conditions and we need to change the microbiology. I went out to the mine site last week with Viola, and we collected some forest soil from the adjacent mine. And we're starting to incubate that with a concoction that includes raw milk, semolina, charcoal, biochar, and molasses. And the reason we're doing such kind of non-complex sources or substrates for the microbes is that I really want them to start chewing through this stuff and get nice and robust. So once we do that, we'll plant these with native plants from Southern Oregon, and then we'll let them grow. And at the end, we'll use molecular techniques to find out what microbes were in here and then what microbes are in here. So Viola opened up one of these, and you can see this was just started last Friday. You can see how gross this already looks. To you, it might look gross, but to me, that's just a beautiful community of microbes doing its thing. So I'm excited. We're going to let this run for 60 to 90 days to see how large the plants get, and then we'll start looking at the soil results, looking at the metals that come out of it, and seeing if we're starting to make a difference. So this project is near and dear to my heart, and I'm really excited about it. So if you guys want to chat, say hello.
She has a sign on it right here. She calls it Strange Brew.
Fuzzy.
Strange Brew. It's my Strange Brew. Are you hoping that the microbes from the Strange Brew will filter down into the mine waste and then start?
So I'm hoping that they'll inoculate the soils. So the whole thing is that, there's two processes going on in the mine. You've got the abiotic reactions that dissolve metals, and then you've got the biotic reactions that produce the substrates for the abiotic reactions. So you really have to just interrupt that coupling. And so that's really what we'll end up looking at. We'll look at how the pH is affected. There's a lot of products that you can buy on the market that you can inoculate soil with, or that you can inoculate plants with. And although some of those products, I will say those products have mixed results. And one of the reasons that I believe they have mixed results is that these microbes are born in a lab, they're raised in a lab, they die in a lab. And when you do that and then you dry them down and as you sell them as a product and then you put them out in the environment, they're just not as adapted. And while I appreciate the message that people are getting out that microbes are important, I also worry that there's not enough quality control on these products. So my idea, and many other people's ideas, I don't mean to take credit for it because it's certainly not a new idea, is to take microbes that are actually living, breathing in a mixed culture that's very difficult to replicate in the lab, grow that up, and then inoculate plots with that. That's going on in a lot of small scales. A lot of developing countries are starting to do this work. And again, that's really why I want to use these products that are commonly available, that is not a very precise mix, so that we can see if it works. And I'm excited to try it out.
Biochar has been widely used in agriculture to improve soil health, water retention, and plant growth yield. For optimal benefits in agriculture, biochar characteristics must be well defined, and the appropriate type of biochar should be selected to meet specific soil needs. Researchers questioned if biochar could be used to increase yields of high-value crops, like garlic, in extremely poor soil conditions. An integrated farm was evaluated to determine the potential agricultural use of low-value biomass cleared on site for wildfire mitigation.
They're integrated farms. They do ranching, they have a lot of timber, and they grow a lot of high-value crops. Now that's a little bit weird for that part of the world. There's some folks who grow garlic, but these are the only folks who are growing garlic in that immediate region. And the reason that they're the only folks growing garlic in that region is that their soils are terrible. We went out to Burch Slope in collaboration with that family, the Heffernan family, and we got some of their soils and we added biochar to it and started asking, can we get increased yields in garlic, which is an extremely high value crop.
And really the intent of our funding to the Heffernans is to see if this material which is being removed on the slopes above their ranch for fuel production purposes, if they could bring it down a few miles away, convert it into biochar and apply it onto their lands to increase their agricultural diversity and productivity. So it's kind of this integrated model of trying to pull the fuel from very nearby and see if the technology and the performance of biochar will actually create that market pull.
Actually segues quite nicely into our next project because I really like this idea of forest to farm biomass movement through biochar, and so we have this other project going on, and the question that we're asking there is, does this forest to farm biochar paradigm make sense economically? Looking at selectively harvesting forests on steep slopes that really need to be thinned, taking that low value biomass and instead of burning it on site, which is business as usual, taking it and putting it to a centralized biochar facility. Then we've got two different production technologies we're looking at. One is microwave technology and one is a pyrolysis from the CAR group. And looking at what it would cost to build a 15,000 ton per year biochar plant, and then we actually went out and had biochar made by those two processes, and now we're testing it to see what the effects are on local soils. Now this is all based in the Klamath Basin, and the Klamath Basin is really this interface between ag, natural forest, tides, and endangered species. So there's a lot of folks who would like to protect the endangered species, especially the fish endangered species, by leaving water in the reservoirs, and then there's a lot of farmers who want to use that water in the reservoirs to irrigate their crops. So it's actually the perfect place to look at whether or not we can save water using biochar, and especially in their soils, which again are just completely awful. So these soils are almost completely sand. When I first saw it, I said, "Oh wow, I didn't realize the beach was in Klamath, Oregon." But apparently it is. These are very sandy soils, so they have trouble holding moisture. So our real question is based off yield yield of alfalfa, which is one of the main crops grown, and one of the most water-heavy grown crops grown in the Klamath Basin, and seeing if we can get an increase in yield by using less water.
We went through and we looked at all the available technologies that could be applied at this scale, either on the farm or in the area, and looked to see if the farm itself could be a producer of biochar for other farmers in the area. So we did a really nice techno-economic kind of a survey of what was available for really kind of a typical sized farm. And as you said, they've got lousy soils, but they do have water. And so we were trying to see if a biochar production would even work out with greenhouse production. what we found was what was killing us was the economics of you really want to do, you're generating so much energy, you want to sell that energy for some purpose or some amount. We couldn't get enough money for the energy or even heat to justify the scale that we wanted to work at with the, but we're getting there. We're improving. The technologies are improving.
Next, we visited a production facility to investigate if biochar can be produced in a carbon reductive pathway, meaning more carbon is stored in the solid biochar than released during the production process. John Miedema evaluated the questions he faces as a biochar producer.
What we have here is a gasifier and a pyrolytic retort, and we wanted to make sure that we had the lowest carbon footprint that we could, and so that's why I chose to use a gasifier as the thermal drive for the pyrolytic retort. So what we do is the gasifier produces a producer gas, and it consumes about 500 pounds of biomass an hour, and it puts out 500,000 BTU. This gasifier was built about 25 years ago by Doug Williams of Fluidine Energy. And then I built that retort out of found material around this log yard. The point of why I came to this facility is because, this is defunct infrastructure that needs to be revitalized. And I think we can use biomass to do that in a localized area. So, biomass needs to be a decentralized energy production, and it can be local sustainable, we can produce a lot of heat. So we can do food drying, we can produce enough heat for industrial processes. So the main point is to try to produce, to prove that there's value in the carbon. We're going to make, in this area, we have the most productive conifer forest in the world, and we're going to make energy in biomass. And my overarching goal was to find value in the a certain fraction of the carbon that's in that energy, because if we can show that there's more value in this carbon material, right? This stuff that's coming out of the retort it has more value than its caloric content. Then, as we build these machines, or these devices or these energy producers in larger, megawatt style, then we're going to harvest tons of this material. And the question is can we do that in a carbon reductive pathway? So we did the carbon accounting for this machine, and the theoretical potential being 3.67 tons of CO2 for every ton of carbon that you harvest. And what we found was that we were sequestering 2.18 tons of carbon for every ton of carbon that we harvest. And this machine, for every 3 tons that goes into it, we make 1 megawatt of thermal drive, 1 ton of this carbon, and the inherent energy to drive the process. So I was very pleased with that result. I was very pleased that we were actually producing a usable material that has more value than its caloric content, and we were doing it in a carbon reductive method. The other aspect is, we've attained 2.18 tons of sequestration, and we're not really even utilizing the heat, right? The heat is getting flared to the side. And if we could start to tie in a methodology where that heat is getting utilized, it's key to the ROI of the device. And it's very scalable, both ways. So if you just want to heat a little greenhouse, you could have it smaller. That to me is the main, one of the main things of the sustainability is that we can't just flare the energy to the side, that we have to find value in that heat. We got to produce this material, use it in a local environment, and revitalize infrastructure. My hope is that we can use, again, this local material to clean up local water, streams, beds and storm water and all of that, and just start to kind of revitalize our local environments, and that this is a wedge. It's not everything. It's not a silver bullet, but it's part of an integrated whole. And that's something that's always been exciting to me, is that it's a central hearth, that we can all gather around. And it's poetic, but it's real.
Biochar has demonstrated the capability of removing organic and inorganic contaminants in water treatment. However, questions remain regarding the long-term field-scale performance, mechanisms for contaminant removal, and how regulations will incentivize treatment investments. Researchers and practitioners outline the questions that act as barriers for biochar implementation in water treatment.
One of the questions that I'd really like answered is how well biochar works in stormwater systems over longer time periods. There's been a whole lot of work doing short-term tests and there's some really promising results. But what I would really like to see is a long-term monitored trial, something like 10 years or more. And obviously there are major barriers to that. Cost is the major one, and also the logistics of running a long-term trial are not easy. But that's sort of the data we need, especially how biochar relates to these bioretention systems, where it's used as a small component of a soil mixture that's meant to support plants, remove pollutants from stormwater, and also hold water. So that's what I would really like to see.
My research focuses on stormwater treatment of metals using biochar. Heavy metals are common contaminants to stormwater through highway, roof, urban, and industrial runoff, and can disrupt aquatic systems at extremely low concentrations. For example, dissolved copper at concentrations as low as 2 parts per billion can inhibit endangered coho salmon's ability to sense and avoid predators. Biochar has proven ability to remove several types of dissolved contaminants, including heavy metals. However, specific mechanisms of removal are not clearly defined. My research seeks to answer the question, what are the fundamental processes controlling copper removal by biochar? Copper removal was investigated in batch studies of hazelnut shell and Douglas fir chip biochar, pyrolyzed at 300, 500, and 700 degrees Celsius. These studies showed increased removal with increasing production temperature and increased removal by hazelnut shells compared with Douglas fir chips. Based on these results, the hazelnut shells pyrolyzed at 700 degrees Celsius were selected for further investigation, including column studies. In column studies, a fixed bed of biochar is placed in a cylinder and water, spiked with copper, is pumped through the media bed. Samples are collected frequently to measure the dissolved copper concentration exiting the filtration media. Copper removal is calculated by subtracting the copper exiting the system from the copper entering the system, integrated over the volume treated. Fundamental copper removal processes will be defined by modeling copper removal, the particle size, flow rate, and volume of the lab scale experiment are designed to predict removal in a pilot scale system. Here, I have 2 columns to investigate the copper removal of biochar and granular activated carbon. The hazelnut biochar, pyrolyzed at 700 degrees Celsius, has shown greater copper removal per mass of filter media and greater treatment volume before dissolved copper began to exit the system. This shows that hazelnut biochar has a greater ability to remove copper or other dissolved metals over a longer period of time, eliminating the frequency for facility managers to replace the filtration media and increasing the lifespan of the system, reducing cost to the site manager.
There are all sorts of water quality issues that biochar can potentially help to address, whether it's nutrients coming out of hog lagoons or metals coming from stormwater runoff or trace contaminants and that sort of thing. But the status quo is that these pollutants are just entering the environment now mostly with no treatment. And in order to put treatment in place, money has to be spent and resources have to be moved around. So really the question is, can we start to put some policies and some regulations in place on contaminants and reducing them to certain target levels, creating mechanisms for monitoring these things, for ensuring compliance? You have to start putting value on these contaminants entering the environment and actually hard coding and regulation.
The synergy of science and industry, that's the theme of this conference today.
And a broad spectrum of participants in the biochar industry attended. Conference attendees were asked to participate in a survey to capture collective knowledge and perspective regarding how we should advance the biochar industry. The goals of the survey were to spark dialogue between biochar researchers and practitioners and evaluate the pathways for growth seen within the industry.
By sector, we endeavored this time to get as mixed a group as possible, and so you can see that about 30% of the attendees are from what I call the research and education sphere, not just fundamental and applied research, but also extension, dissemination, the all-important job of how to use biochar and how to apply it in practice. Another 30% of the biochar producers and technology suppliers. As you all know, there's some overlap there. Many of the technology suppliers are also producing biochar products. And we've attempted to draw in people from other aspects of the industry, biomass supply, forestry, ag, landscape, urban, organic recycling, other aspects which provide both feedstocks and have a need for biochar. And about 10% of the attendees are from the policy sector.
The first survey question asked participants to evaluate the importance of individual soil health benefits for expanding biochar markets. Survey results indicated that all soil health benefits examined were important. pH adjustment had the lowest relative importance compared with water and nutrient retention, soil structure improvement, crop productivity improvement, and soil carbon addition. The importance of soil benefits of biochar are related to site-specific soil deficiencies and need to be evaluated on a case-by-case basis. Therefore, the spread of survey results is predictable for soil benefits. The second question evaluated what was missing to help propel the biochar industry forward. Survey results again showed spreading between the needs evaluated. Lower prices and increased supply were identified least frequently as needed for biochar industry advancement. Policy support and incentives was identified most frequently as missing to propel the industry, followed closely by technical application information and grade specifications and better production technology. There appears to be a consensus that better characterization and documentation of biochar is needed, paired with policy support. Next, survey participants were asked which are the most important attributes and benefits of biochar to promote to society. Again, survey results were spread between biochar attributes of mitigation of climate change, rural economic development, agricultural soil productivity and water efficiency, recycling and reuse of biomass, and pollution mitigation. Given the diversity of survey participants from biochar supply, production, and agricultural and remediation applications, it is expected that individuals value biochar attributes in their respective fields. However, lack of consensus makes it difficult to identify pathways forward within the industry. The final question asked about how important each biochar producer type will be in 10 years. From small-scale boutique producers producing a few hundred tons per year to large producers making tens of thousands of tons per year, each producer type was evaluated as important by survey participants. Producer types evaluated included local boutique and medium producers, retrofitted biomass boilers, and large producers with tight technical specifications. Again, spreading of survey results makes it difficult to identify the optimal producer type for the advancing biochar industry. David Smith summarized the survey results at the final plenary session of the USBI conference, where a panel of experts and audience of conference attendees responded to the spread results. Overall, there is a consensus for need to focus efforts, develop a trade association, and define biochar characteristics for targeted end-use applications.
We had about 230 responses, and we've got such a broad range of folks here. Everyone that from just sort of heard about biochar, was curious about it, the people that are large-scale producers.
Wow, everybody's sort of on all these questions. That's both strength and weakness. It's a strength in that we have a lot to contribute to a lot of different problems. It's a weakness in that it makes it hard for us to focus.
It seems like looking at the diversity of responses and thinking about where does the industry go forward and how. I do a lot of work in the public sector. I work for the Department of Forestry, and I represent the issue of biomass and forestry. And I think what works in forestry and biomass is if there's a compelling story, there's a compelling narrative that you can connect to a resource condition or need, and there's a solution that one can present either to a funder or to a policymaker. And I think what these responses show is that we don't really have that singular narrative yet. We don't have a single story. We have multiple stories. And that's what we need to do to connect with policymakers, to connect with funders, to connect with folks that might be regulators, that we're seeking their help to solve a particular problem. We have to sharpen up that proverbial pencil so that the narrative is really clear about what it is we're asking for and why, and what is that problem that we're solving. And I think at this point, these responses indicate that we think biochar solves a lot of different problems, and there's a tremendously wide field of opportunity. But I also think that what it indicates is that collectively we have to focus.
When I go to tell the story to people, what this is actually, it's too diverse to get the story across. And so what we need to do is actually get the material in the ground or into a place where it's cleaning up the toxin and start to tell these stories where we know it's, but to not get so diverse and so broad that the story gets confused. And so we find some early wins, we do more field applications with good data sets and build up these things that we know it works, and we look at these other benefits. And that's how, for me, that's how we get the story across.
We actually have a basis. I think as a community, we need to use the tools we have at hand and build on those. We have a classification system. My recommendation moving forward is that we use the organizational tools and things that we have available and go further with the full idea of characterizing chars in the specific applications.
Maybe you could categorize the chars by which function do you want that char to perform, and then make a list of the different qualities and properties of the chars that can achieve those functions, and that's a great educational tool, and it kind of addresses this wide variety of chars out there.
We've got an almost infinite variety of biochar types, an infinite variety of soil types, an infinite variety of climate scenarios, of crops, of agronomic environmental applications, and there's been talk, well, we need studies to, localized studies to address the problem here or there, Okay, we can approach this anecdotally, but we're going to move at a snail's pace. How do we synthesize across the literature? And I've looked around at the papers we've seen here, it worked here, it was great. Here we didn't get any response at all. We saw water improvement here, we saw nothing over here. From my perspective, I think the only path forward is system modeling approach. We need to have biochar modules integrated into cropping system models that can predict and work with that diversity. We need them integrated in water models, equipped. We are working at Iowa State with APSIM and have built a biochar module in APSIM. It's still in its early stages, but I'm convinced that systems modeling is the only path forward.
Let me suggest the focus, if you're looking for a focus, is food and health, or healthy food, and everything else dovetails into it, falls into line. I don't know anybody in here who doesn't eat. I don't know anybody out in the public who doesn't eat. The public is interested in food and more in quality food. By that I mean nutrient-dense food. You can't sell biochar to farmers. You can't sell it to the public. You can only sell it in terms of what they see it doing for them, which is in their food and their health.
There's a problem with the rate we burn fossil fuels. Carbon in, carbon out. It's causing climate change. But pyrolysis can convert waste to energy. Carbon in, energy out, and stable char remains. Heating in an oxygen-free environment will produce a stable form of carbon called biochar. while producing bio oil, heat, and energy. Biochar will go far to reduce carbon emissions. It can also absorb many metals and nutrients. Biochar is not all the same. I am working to characterize biochar, optimal to remove metals from stormwater. This must find a balance with other biochar functions to advance sustainability. There's copper in concrete paths dissolving into the rivers. It's affecting endangered salmon, but not their hearts or livers. Their sense of smell is hindered, so they don't avoid predators. We need to reduce the copper available as dissolved ions. Adsorb the Cu2+. Adsorb the Cu2+. I'm using biochar to filter stormwater. This is the key. Biochar is pyrolyzed from organic waste to create heat and could control the fate of heavy metals run off to rivers. Adsorb the